There is a star out there, so enormous that if it were placed in the position of the Sun, everything around it would vanish. From Mercury to Mars, Saturn's rings, the surface of Jupiter, all would be swallowed whole. The space between Jupiter and Saturn would be nothing but the skin of this star, turning the entire solar system into a memory inside a searing gas sphere. This is not science fiction. Stevenson 2-18, currently recognized as the largest star observable in the universe, almost slipped past our notice. Located 20,000 light-years from Earth, hidden in the Scutum constellation, it has quietly existed beneath dense layers of dust and gas, invisible to visible light for decades. Only when astronomers trained infrared telescopes on a specific star cluster did they realize a massive object was pulsing, radiating energy far beyond any nearby star. What makes Stevenson 2-18 astonishing isn't just its size. Physics theory once set limits on stars, seemingly preventing them from growing this large. Yet there it is, defying models, challenging our understanding of stellar evolution. Its radius is roughly 2,150 times that of the Sun. If the Sun were the size of a basketball, Stevenson 2-18 would tower over a 20-story building. The volume contained within it is equivalent to 10 billion suns. The star also shines with energy 436,516 times that of the Sun, yet its surface temperature is only about 3,200 Kelvin, nearly half that of the Sun, producing its characteristic deep red glow instead of the familiar yellow-white. The surrounding dust shell not only hides it, but tells a story of massive mass loss, unstable outer layers, and clear signs that Stevenson 2-18 is entering the final stages of its life. Its discovery story is as colorful as a detective novel. Charles Bruce Stevenson, an American astronomer, stumbled upon a cluster of red supergiants during a deep infrared survey. Within the Stevenson 2 cluster, one star was initially labeled number 1, later changed to number 18, after its position in the outer group was confirmed. The various names Stevenson 2-18, ST2-18, Stevenson 2 DFK1 reflect the evolving understanding of this stellar giant. Though only about 17 million years old, Stevenson 2-18 lives fast and dies young. With a mass millions of times that of Earth, the star has only a few million years left before ending its life in a brilliant supernova, a powerful testament to the grandeur and fragility of the universe. A defining feature of red supergiant stars is mass loss. Stevenson 2-18 is shedding material at a rate of approximately 1.35 times 10⁻⁵ solar masses per year. It may sound small, but in reality, every 3 years, it loses an amount of matter equivalent to the mass of Earth. This material does not simply vanish into nothingness. Instead, it forms an extended shell of gas and dust around the star, and it is precisely this shell that produces the infrared signature, allowing astronomers to detect it. The outflows from Stevenson 2-18 also reveal much about the star's outer atmosphere. Natural microwave lasers appear when molecules in the stellar wind water vapor, silicon monoxide, and others are excited by radiation from the star. The presence of these material clumps signals the extreme conditions around the star, with temperatures, densities, and radiation levels that would instantly destroy any object we could imagine sending there. Before Stevenson 2-18, the record for the largest star belonged to Scutum. Discovered by German astronomers in 1860 at the Bonn Observatory, it was once considered a giant with a radius about 1,700 times that of the Sun, capable of containing nearly 5 billion suns by volume, a figure that stretches our imagination almost to its limit. But astronomical measurements are never simple, especially for objects thousands of light-years away. Any error in distance translates directly into errors in size. The parallax method, based on the apparent shift of a star against background stars as Earth orbits the Sun, provides the most precise distances. Yet for stars so far away, the precision must be extraordinary. When ESA's Gaia spacecraft began releasing highly accurate positional data, astronomers immediately revised the distances to many famous stars. The results were astonishing. Scutum turned out to be much closer than previously thought, about 5,871 light-years instead of over 9,000. A closer distance meant a smaller size. Its revised radius was only about 99 times that of the Sunday. Still enormous, but no longer record-breaking. The situation is further complicated by the fact that astronomy is rarely definitive. Different measurement techniques yield different results. Infrared observations, optical measurements, or theoretical models based on luminosity and temperature can all differ. Errors can reach 50% or more, meaning the title of largest star is constantly changing as new data appear and older measurements are recalibrated. Several other candidates also compete for this title. NML Cygni, heavily obscured by dust in the Cygnus constellation, has an estimated radius between 1,183 and 2,770 times that of the Sunday. VY Canis Majoris, perhaps the most famous red supergiant, has been measured from 1,420 up to over 1,900 solar radii. WHG 64, located in the Large Magellanic Cloud outside the Milky Way, also presents challenges due to its extreme distance. The underlying issue is that these stars are surrounded by thick shells of gas and dust, making it difficult to distinguish the star itself from the surrounding material. Unlike our Sun, with its well-defined surface, red supergiant stars have fragile outer layers that gradually extend into the surrounding space. Determining their radius becomes more a philosophical question than a simple measurement. What is certain is that all of these stars represent the upper limit of stellar-sized cosmic giants beyond the imagination. They are red supergiants, with spectral types K or M, indicating surface temperatures below 4,100 Kelvin. They have entered the final stages of life, having exhausted hydrogen in their cores and moved on to fusing heavier elements. This fusion produces less energy per unit mass, for the star to expand dramatically to maintain pressure against gravitational collapse. It is this expansion that creates the stellar monsters we call giants. A star born with a mass of roughly 25-40 solar masses can balloon to seemingly absurd sizes. Its outer layers become so tenuous that their density is lower than air on Earth, and in some regions, nearly approaches laboratory vacuum. In theory, a spacecraft could pass through these layers without instantly vaporizing, though the radiation would still be lethal to any living being. Another surprising aspect is that these giants are not truly massive in proportion to their size. Scutum, despite having a volume equivalent to 5 billion suns, has a mass of only about 25-40 solar masses. Most of its volume is extremely diffuse gas. Stevenson 2-18 is likely similar, though its precise mass remains uncertain. In the stellar universe, size and mass are not linearly proportional, especially for these fading giants. Temperature is another unexpected factor. One might assume the largest stars must be the hottest, but in fact, the opposite is true. Our Sun sits around 5,500 Kelvin, while Stevenson 2-18 is only about 3,200 Kelvin. This cooler temperature is what gives these giants their deep red color rather than yellow or bluish-white. According to the Stefan Boltzmann law, total energy output depends on both temperature and surface area. These giants compensate for lower temperatures with enormous surface areas, shining with luminosities hundreds of thousands of times that of the Sunday. The hunt for the largest star continues as telescope technology steadily improves. Infrared surveys are particularly important, as they penetrate the dust that obscures visible light. The James Webb Space Telescope, with its powerful infrared capabilities, promises clearer views of the surfaces and environments of these giants. And why do astronomers devote so much effort to these measurements? Not merely from human curiosity about extremes, the biggest, brightest, most distant, but because these stars tell us fundamental stories about the laws of physics. They are natural laboratories, where matter behaves under conditions that Earth could never replicate. The process is occurring inside Stevenson 2-18, are where the elements that seed the next generation of stars and planets are forged. The iron in your blood, the calcium in your bones, the oxygen you breathe, all were created inside stars like this. Understanding how stars reach such extreme sizes helps us gain a clearer picture of stellar evolution. Why do some stars become red supergiants while others end their lives differently? What determines the maximum size a star can reach? Are there physical limits that we have yet to discover? Every new measurement, every adjustment in distance, every refined model brings us closer to the answers. At present, Stevenson 2-18 holds the record for size, based on observational evidence. But this answer comes with large margins of error and numerous caveats. Measurement uncertainties are significant enough that tomorrow another star could take the title. NML Cygni could reclaim it if its distance turns out to be at the far end of current estimates. An entirely undiscovered star, hiding somewhere in a dusty corner of the galaxy, could surpass anything we've ever found. What is certain is that stars cannot grow indefinitely. Physics imposes limits. There is a boundary between gravitational collapse and radiation pressure. Cross these limits, and a star becomes unstable, shedding its outer layers violently or even being completely destroyed. The giants we observe today may already be teetering on that edge, held together only by a thin veneer of stability. Their lifetimes are also short on a cosmic scale. The processes that allow them to expand to enormous sizes, fusing heavier elements in their cores, simultaneously deplete nuclear fuel rapidly. When the fuel runs out, what happens next? The answer is the most violent and energetic phenomena in the universe. A supernova explosion can outshine an entire galaxy for a brief moment, while producing elements that cannot be created in any other way. The final moments of red giants make their already brief lives seem almost gentle compared to the destruction to come. When a red supergiant exhausts its fuel, the core collapses within milliseconds, triggering a supernova explosion that releases in seconds more energy than the sun will emit over 10 billion years. Shockwaves tear through the outer layers, propelling material to a significant fraction of the speed of light and heating it to billions of degrees. Within a few weeks, a dying star can shine brighter than hundreds of billions of ordinary stars combined. But with the most extreme red supergiants, the story is even stranger. They do not always depart quietly. VY Canis Majoris, for example, has been losing mass at an extraordinary rate every 6 years, shedding an amount equal to Earth's mass. Recent Hubble observations revealed giant arcs and clumps of ejected material surrounding the star, with some clumps as large as the entire solar system. These are not gentle stellar winds, they are violent eruptions, flinging chunks of matter at hundreds of kilometers per second. This is significant because it suggests that extreme red supergiants may self-destruct before they even have a chance to explode as supernovae. Imagine a star so massive and luminous that its own radiation pressure is strong enough to tear it apart. Photons from the core push outward with more force than gravity can pull inward. Surface material becomes unbound, expelled in colossal eruptions. Over time, the star loses so much mass that the core may no longer be heavy enough to trigger a supernova when nuclear fusion ceases. This process, known as superwind mass loss, may explain why we rarely observe red supergiants larger than Stevenson 2-18. There seems to be a natural ceiling on stellar size. It's not that stars cannot grow bigger, but that once they reach that threshold, they begin to tear themselves apart. The lifetimes of these giants are extremely short on a cosmic scale, only 10 to 20 million years. Compared with the Sun, which has burned steadily for 4.6 billion years and will last another 5 billion, red supergiants consume energy at an extraordinary rate. They burn through fuel thousands of times faster than smaller stars, racing through their entire life cycle in the blink of an eye. While smaller stars are still in middle age, UY Scutum might explode within a few million years. Stevenson 2-18 could cross the finish line even sooner. In fact, both may have already exploded without our knowledge, since their light takes tens of thousands of years to reach Earth. Right now, A brilliant star may be shining in someone else's sky, signaling the death of a giant, while we are still waiting for the news from the darkness. What triggers the final collapse? It's a story about the limits of nuclear fusion. A star like the Sun fuses hydrogen into helium in its core throughout its main sequence lifetime. But giant stars do not stop there. When hydrogen is exhausted, the core contracts and heats up, fusing helium into carbon, carbon into neon, neon into oxygen, oxygen into silicon. Each stage produces less energy and burns faster than the previous one. Hydrogen may burn for millions of years, but silicon fusion lasts only about a day. The core of a dying red supergiant resembles an onion, with layers of different elements burning at different depths. The outermost layer burns hydrogen, beneath it helium, then carbon, neon, oxygen, and silicon. Each layer becomes denser and hotter toward the center. At the very core lies iron, the final stage. Iron fusion does not release energy. It consumes it. When the core becomes iron, the star's energy source shuts down entirely. What happens next occurs faster than the blink of an eye. Without supporting pressure, the iron core collapses. In less than a second, an Earth-sized iron mass is compressed to a diameter of roughly 20 kilometers. Extreme density forces protons and electrons to merge into neutrons, releasing a flood of neutrinos that carry away most of the explosion's energy. The outer layers fall onto the neutron core at nearly a quarter of the speed of light, colliding and rebounding, creating shockwaves that tear the star apart. The supernova is the visible light from this catastrophic collapse, the final breath of a star that once dominated the space around it. For Stevenson 2-18, the explosion would be unimaginably spectacular. Observed from a few hundred light-years away, the supernova would shine as brightly as a full moon. Even from 20,000 light-years, it could be visible in daylight for several weeks. The exploding debris would glow for months, gradually fading as it cools and merges into the interstellar medium. Most importantly, this material carries all the elements forged over the star's lifetime, and in that final moment, carbon, oxygen, nitrogen, silicon, calcium, iron elements that barely existed when the universe began. The first stars contained only hydrogen and helium. Everything heavier originates from nuclear fusion in stars and supernova explosions. The atoms in your body, the iron in your blood, calcium in your bones, phosphorus in your DNA were all forged in stellar cores like Stevenson 2-18 and spread across the galaxy over billions of years through supernovae. You are literally made from the stardust of stars that have died. This cosmic cycle continues to this day. The material ejected by red supergiants does not vanish into nothingness. It forms massive clouds of gas and dust that eventually collapse under their own gravity to create new stars and planets. The next generation inherits the chemical legacy of the previous one, beginning with a richer mix of elements, allowing for complex chemistry and ultimately, life. Some supergiants do not even explode as standard supernovae. The most massive stars can collapse directly into black holes, their cores so heavy that nothing can halt gravitational collapse. Their outer layers fall inward and disappear past the event horizon, carrying their elements with them, leaving behind a black hole that recycles almost no matter back into the universe. Others may become hypernovae, explosions more powerful than ordinary supernovae, sometimes accompanied by gamma-ray bursts, capable of sterilizing planets tens of light-years away. A star's fate depends on its mass, rotation speed, and magnetic field strength factors we are still struggling to measure accurately in these distant giants. Uncertainty extends to the remnants they leave behind. A typical red supergiant leaves a neutron star, an object so dense that a teaspoon of its matter weighs as much as Mount Everest. Neutron stars spin incredibly fast, sometimes hundreds of times per second, emitting beams of radiation that sweep through space like cosmic lighthouses. We detect them as pulsars, precise cosmic clocks that helped astronomers discover the first planets outside our solar system. But the largest supergiants may skip the neutron star stage entirely, collapsing straight into black holes. The core of Stevenson 2-18 could be massive enough that no neutron degeneracy pressure can prevent total collapse. When it explodes, its core might vanish into a black hole while the outer layers still fall inward. Stellar mass black holes like these also have fascinating fates. They do not remain stationary, but can merge with other black holes in violent collisions, shaking the fabric of space-time and sending gravitational waves across the universe. Observatories like LIGO have detected dozens of such mergers, each marking the final chapter in the lives of long-dead giant stars. The existence of stars like Stevenson 2-18 also challenges other theoretical limits. How did they form in the first place? Standard star formation theory suggests that radiation pressure should prevent gas clouds from collapsing into such massive objects. The very light emitted by the forming star would blow away in falling material before it could accumulate. Yet these monsters exist, indicating that our models of star formation are incomplete. One possibility is runaway mergers in dense star clusters. Stevenson 2-18 may not have been born as a single massive star but grew by accreting smaller companions in a crowded gravitational environment. The Stevenson 2 cluster contains multiple red supergiants within a relatively small volume of space, suggesting conditions favorable for the formation or evolution of extremely massive stars. Another factor is metallicity, the abundance of elements heavier than helium. Today, stars in the Milky Way form from element-rich gas, inherited from previous generations of supernovae. This enriched gas cools faster, allowing large clouds to collapse more easily and form higher-mass stars. In contrast, the early universe, composed almost entirely of hydrogen and helium, likely did not produce red supergiants like those we see today. These factors are crucial for understanding galaxy evolution. Though rare, massive stars profoundly affect their surroundings. Their intense radiation ionizes giant gas clouds, creating luminous nebulae across cosmic distances. Stellar winds and supernova explosions inject enormous energy into the interstellar medium, triggering new waves of star formation while blowing gas out of small galaxies. In the sky, giant stars shine like natural laboratories, where matter is pushed to extreme limits. Million-degree temperatures, radiation pressure, magnetic fields interacting with convective flows. Each phenomenon challenges our understanding of the universe. Every measurement, every spectrum, every refined distance adds another piece to the stellar model astronomers hold in their hands. Yet determining the true size of these colossal objects, distance becomes the enemy. A 20% error in distance estimation can double the radius uncertainty to 44%. For stars 20,000 light-years away, measurement becomes nearly an impossible challenge. The Gaia spacecraft has opened a new era for nearby stars, but distant objects like Stevenson 2-18 continue to perplex astronomers. The parallax method, the apparent shift of a star's position as Earth orbits the Sun, works perfectly for nearby stars. For stars 20,000 light-years away, the shift angle becomes so tiny it is nearly undetectable. On top of that, light must pass through interstellar dust and gas, which scatter and absorb it in unpredictable ways. The zone of avoidance regions of the sky obscured by the Milky Way's disk makes measurement even more difficult. Stellar temperature, inferred from spectra, is also not simple. Cool giants with complex atmospheres and strong stellar winds form molecules in their outer layers, creating absorption bands that complicate spectral interpretation. Does the light we observe reflect the visible surface, or has it been altered by surrounding dust and gas? Stellar variability adds another layer of difficulty. Stevenson 2-18 does not remain still. It pulses, its surface rising and falling like slow-moving waves. A radius measured today may differ by hundreds of millions of kilometers from a measurement next year. Which value is the real one? Some astronomers take an average, others take the maximum. These choices directly influence how stars are ranked. Infrared observations and interferometry help penetrate dust and increase resolution. But even here, assumptions about composition, density, and dust distribution remain critical. A small change in distance estimate can overturn everything. Scutum is a prime example, once thought to have a radius around 1,700 solar radii. Gaia data showed it is closer. A shorter distance, lower luminosity, smaller calculated radius, down to roughly 755 solar radii. The star itself has not changed, only our instruments and models have become more precise. This reminds us of a fundamental truth in astronomy. Every measurement depends on a model. We cannot lay a ruler directly on a star. Instead, we observe light, spectra, sometimes angular diameter, and then use theoretical models to infer radius and luminosity. Each research team, with its own assumptions, produces a slightly different picture of the same star, but all contribute to expanding our understanding of the vast universe. The assumptions astronomers make, seemingly small, ripple through every calculation. One team may rely on chemical composition based on position in the Milky Way, another accounts for rotational effects, a third handles convection differently. The final results, radius, luminosity, all bear the imprint of these choices. Published uncertainties attempt to capture the unknowns, but cannot fully account for systematic biases hidden within the models. Then there is Stevenson 2-18. Its strong infrared emission signals something unusual nearby. A massive shell of ejected material, stellar winds varying dramatically in density and temperature. We are not just measuring the star, but the star and its extended atmosphere and surrounding material. The boundary where the star ends and space begins becomes astonishingly blurred in a sprawling red supergiant. The cluster in which Stevenson 2-18 resides provides context that helps reduce some uncertainties. Knowing it belongs to the same cluster as other red supergiants, we can assume a common distance. By comparing relative luminosities, we can infer relative brightness. This does not eliminate distance errors entirely, but at least enables cross-checks. This technique, main sequence fitting, places the cluster stars on stellar evolution models. The cluster's age, about 17 million years, constrains the initial mass of the surviving giants. The red supergiants we see today were born with 25 to 40 solar masses, now standing on the edge of brief, violent final stages. Stellar evolution is not uniform. Rapid rotation stirs the core, brings fresh hydrogen inward, heats faster, and sometimes stars skip the red supergiant phase entirely. Slow rotation, or lack thereof, allows stars to expand and cool, becoming red giants. Metallicity also shapes the process. Metal-rich stars lose mass quickly through stellar winds, stripping outer layers before the star can swell. Even though the Stevenson 2 cluster is metal-rich, red supergiants still form, and the detailed effect of metallicity at extreme masses remains debated. Additionally, companions sometimes play a role. Binary stars, mass transfer, mergers, all produce evolutionary paths that single star models cannot predict. Stevenson 2-18 may have swallowed a satellite, and the dense cluster environment makes close encounters relatively common. Observing the stellar wind, we glimpse the star's future. Stevenson 2-18 loses roughly 0.0000135 m per year, about 13 Earth masses, equivalent to the Sun's mass over 74,000 years. This loss cannot continue indefinitely. When the mass drops below a critical threshold, the star's structure changes fundamentally. But will it explode before or after reaching that point? Stellar winds do more than remove mass. They carry away angular momentum, slowing rotation, while enriching the interstellar medium with heavy elements, preparing the next generation of stars. Nitrogen, carbon, oxygen, the products of nuclear reactions deep within stars are blown outward at hundreds of kilometers per second. When they collide with slower-moving gas from previous ejections, shockwaves erupt, heating the collision zones to millions of degrees and producing X-rays detectable from Earth. These collision regions create complex, nested shells, like a story written in matter around evolved giant stars. Hubble images of similar stars reveal intricate structures, loops, arcs, dense knots of gas, each detail narrating the history of mass loss, changes in wind velocity, and asymmetric pulsations. Stevenson 2-18, buried deep in dust, has yet to reveal such clarity. But if we could observe it, we would see a universe creating dust within stellar winds, cosmic grains emerging from hot gas. Canis Majoris has shown that a red supergiant can produce enormous dust grains, like boulders between the stars. Stevenson 2-18 may do the same, explaining its intense infrared glow. These dust grains will eventually disperse, providing raw material for future stars and planets. The carbon in your body, the oxygen you breathe, the iron in your blood, all in part originating from red giants like Stevenson 2-18. These giants are massive element factories, turning hydrogen into everything up to iron. Then, when they explode as supernovae, creating gold, platinum, uranium, spreading heavy elements throughout the galaxy. Without them, the universe would remain hydrogen and helium, no rocky planets, no chemistry, no life. The existence of extreme stars like Stevenson 2-18 is essential for cosmic chemical evolution. Their brief lives and brilliant deaths sow the foundation for complexity. In this cosmic panorama, radius measurement errors seem almost trivial. 2,000, 150, 2,000, or 1,800 solar radii, whichever the number. It does not diminish the extraordinariness of Stevenson 2-18. It remains a colossal object, challenging the physical limits of stars, and the effort to refine these measurements drives technology, theory, and benefits the entire field of astronomy. The future promises even more powerful tools. Extremely large telescopes in Chile will excel in light gathering and resolution. Infrared space telescopes will peer through dust, and gravitational waves may one day capture the moment of a supernova, revealing the final seconds and the resulting black hole. Until then, we work with available data, analyze carefully, cross-check multiple methods and models, measurement by measurement, gradually revealing the picture, narrowing uncertainties, and increasing confidence. Even while some doubt remains, Stevenson 2-18 stands among the largest stars ever discovered. It will die in a brilliant display, perhaps within a few 100,000 years, its supernova outshining entire galaxies, leaving behind a black hole that will endure long after the sun has vanished. A permanent scar in space-time, marking the place where one of the largest stars ever burned, and the surrounding region, the 17 million-year-old cluster, tells its own story, the children of the same molecular cloud, all acting as cosmic laboratories, where the differences between them reveal how stars evolve. Stevenson 2, the star cluster where Stevenson 2-18 resides, is home to about 26 red supergiants, an extraordinary collection of these rare cosmic beings. 17 million years ago, a massive cloud of gas and dust collapsed under gravity, fragmenting into hundreds, even thousands of protostars. The most massive stars evolved the fastest, burning through their hydrogen, swelling into red giants, and now stand on the brink of death. Smaller stars in the cluster remain quietly on the main sequence, burning hydrogen for billions more years. For astronomers, Stevenson 2 is a perfect laboratory. Each red supergiant, in the same evolutionary stage, at the same distance, with similar initial composition, allows for comparison of subtle differences, which loses mass faster, which rotates more quickly, which swells larger or smaller. Each variation reveals how minor factors influence late-stage evolution. One star may go supernova next year, another may persist for hundreds of thousands of years. Individual fates cannot be predicted, but the ensemble enables theory testing. Do the number of red supergiants match the cluster's age and mass? Does the distribution of properties fit the models? If not, our understanding must be revised. The Stevenson 2 cluster lies in the Scutum crux spiral arm, where massive molecular clouds continuously form star clusters. Many young clusters are obscured by dust, visible only in infrared. Stevenson 2 is fortunate to occupy an observable location. Imagine, if each similar cluster contains 24 red supergiants. The Milky Way today hosts hundreds or thousands of dying giant stars, each destined to explode within the next million years. On average, a supernova occurs roughly every century. Many are hidden by dust or on the far side of the galaxy, but detection capabilities are steadily improving. The next supernova will be observed with tools unimaginable to previous generations: gravitational waves, neutrinos, X-rays and gamma rays, and optical light, all capturing the star's final moments. But these stars are inherently unstable. Mass is lost in episodes. Eruptions occur repeatedly, and internal structure shifts. Each significant mass loss event subtly adjusts the star's evolutionary trajectory. If enough outer layers are stripped, the core is exposed early, and the physics within changes completely. Some red hypergiants may skip the supernova phase, collapsing directly into black holes, vanishing in a blink. Others may undergo a supernova before core collapse, forming a black hole, or lose enough material to leave only a neutron star. The outcome depends on mass, rotation rate, and the amount of mass lost during the red supergiant phase. Stevenson 2 to 18 loses mass rapidly, over 0.0001 m per year. In 10,000 years, about 0.1 solar masses. In 100,000 years, nearly a full sun disappears into the cosmos. This mass loss shapes the star's ultimate fate. But the material does not vanish into nothingness. It expands into a surrounding nebula, mixing into the interstellar medium, ready to form the next generation of stars and planets. The heavy elements Fe, C, that Stevenson 2 to 18 ejects today may billions of years from now become planets where life begins. Directly tracking the material that Stevenson 2 to 18 ejects remains a major challenge. Dust obscures our view, and the surrounding environment is complex and constantly changing. Observations across multiple wavelengths reveal different aspects. Infrared unveils hot dust close to the star. Radio detects molecules farther out, and visible light reflected off dust forms reflection nebulae. To construct a complete picture, astronomers must combine data from multiple observatories across the electromagnetic spectrum. Among these techniques, Maser's natural microwave emissions, analogous to lasers, are particularly useful. Molecules like silicon monoxide or water in the star's surrounding atmosphere, under the right conditions, emit bright masers detectable in radio observations. These bright spots reveal velocity and material flow. Stevenson 2 to 18 exhibits strong maser emission, signaling dense molecular gas close to the star. The material is not simply drifting, it is accelerated outward, driven by radiation pressure and possibly by shock waves. Photons impart momentum to dust grains. Gas coupled to dust via collisions is dragged along. The efficiency of this mechanism depends on grain size, gas-to-dust ratio, magnetic fields, and turbulence. To understand this better, scientists simulate Stevenson 2 to 18's environment in 3 dimensions over tens of AU, modeling interactions between gas and dust under radiation, gravity, and hydrodynamics. Supercomputer calculations run for weeks, generating terabytes of data, which are then compared with actual observations. When the models match observations, confidence in understanding increases. When they don't, either the models or the observations must be revised. This iterative process guides new observations, gradually clarifying the mechanisms at work. But Stevenson 2 to 18 does not exist in empty space. It is part of a galactic ecosystem, where stars, gas, and dust continuously interact. Material ejected by the star enriches the interstellar medium with heavy elements. Other stars absorb some of this material. Previous supernovae compress interstellar gas, creating conditions for new star formation. Massive stellar winds carve bubbles and cavities in molecular clouds. The cycle of birth, growth, death of stars occurs over billions of years, gradually increasing a galaxy's metallicity. Long ago, galaxies contained only hydrogen and helium. First-generation stars, formed from primordial gas, lived short lives, exploded, and created the first heavy elements. Second-generation stars absorbed these elements and produced new ones, then exploded again. Successive generations progressively increased metallicity. The Sun is probably about the 100th generation, containing elements forged through dozens of prior stellar generations. The Earth, our bodies, the atoms we carry, all originate from stars that exploded billions of years ago. We are literally made of stardust. Stevenson 2-18 continues this ancient cycle. Right now, in its core and inner layers, it is synthesizing heavy elements through nuclear reactions. When it eventually explodes, those elements will be spread across light years. Some will form new stars and planets. Perhaps, billions of years from now, an intelligent being will walk on a planet containing atoms from Stevenson 2-18, look up at the night sky, and wonder about the cosmic origins of their existence. This is not poetry. It is the inevitable result of galactic chemical evolution, a process that takes tens or hundreds of millions of years to complete. While we observe, measure, and model, striving to understand these extraordinary beings before they vanish, Stevenson 2-18 could explode tomorrow or persist for another 100,000 years. By cosmic standards, its lifespan is but the blink of an eye. Thousands, even millions of humans have gazed at the patch of sky containing Stevenson 2-18 without ever knowing. It is invisible, hidden behind dust, detectable only through sensitive infrared instruments. Imagine a star so large that, if placed at the center of the solar system, its surface would extend beyond Jupiter's orbit. Massive, yet invisible, a characteristic that defines astronomy. The universe contains countless wonders imperceptible to the naked eye. Atmospheres block most electromagnetic radiation, dust obscures vast regions, and distance reduces bright objects to faint pinpricks of light. We are like blindfolded observers, touching small portions of a colossal elephant, speculating about the whole from limited fragments. Yet we are making progress. Every new telescope, every improved detector, every sophisticated analytical technique reveals a new layer of information. Infrared, barely feasible 50 years ago, now penetrates dense dust where optical telescopes see nothing. Interferometry combines multiple telescopes to achieve unprecedented resolution. Adaptive optics compensate for atmospheric turbulence, delivering nearly space-quality images from the ground. In the 1960s, Stevenson 2-18 was completely invisible, a faint infrared glow, buried in background noise. Only with modern arrays, advanced data processing, and careful analysis can we recognize it as an extraordinary object. And there is so much more still hidden, awaiting the next technological breakthrough. How many stars larger than Stevenson 2-18 lie deep within unexplored dusty regions? The Milky Way spans 100,000 light-years, and we have surveyed only a fraction, enough to detect a few extreme red giants. The future promises more sensitive, automated surveys. AI may identify patterns that humans might overlook, gradually completing the census of extreme stars. Yet absolute completeness will never be achieved. There will always be stars we have not detected, stars that exploded before we aimed our telescopes, or stars in galaxies too distant to observe. Astronomy operates at the limits of what is observable, a paradox when studying rare phenomena. Success requires luck, timing, location, and the right instruments. Stevenson 2-18 may have exploded centuries ago, and the light we see today is merely a cosmic memory, with no way of knowing we are witnessing an event that has already passed. In the vast expanse of space, Stevenson 2-18 quietly burns the remaining fuel in its core, as if buying a few million extra years before catastrophe arrives. Around it, the cluster hosts its fellow red supergiants, none larger, but all sharing the imprint of a common origin. Observing the group, comparing ages, chemical composition, mass loss rates, and evolutionary stages, reveals the broader picture, where universal physical laws rise above the randomness of the cosmos. Their spectra tell their own stories. Absorption lines reveal elements, temperatures, and velocities of material. Emission lines indicate outflowing gas, sometimes at hundreds of kilometers per second. Massa's amplification of waves at specific wavelengths by molecules in the surrounding envelope provide an additional diagnostic window. Stevenson 2-18 emits strong signals from water vapor and silicon monoxide, demonstrating a high concentration of material close to the star. It may seem odd to think of water vapor surrounding a star, but at a surface temperature of around 3,200 Kelvin, molecules can survive. It is hot enough for any solid matter to evaporate immediately, yet cool enough for chemical bonds to form, creating a natural chemical laboratory within the star's gaseous layers and envelope. The labyrinth of silicon monoxide reveals that dense gas is being ejected, not leaking uniformly, but flowing along structured channels. The geometry of these flows is crucial, determining how matter escapes the star's gravity and its subsequent fate in the universe. All of this data is translated into computer models, where input parameters mass, composition, rotation evolve according to physical equations. Nuclear fusion in the core generates energy and new elements. Convection transports heat and material. Radiation pressure counters gravity. Each model tracks thousands of variables simultaneously, solving nonlinear equations that combine nuclear physics, thermodynamics, hydrodynamics, and radiative transfer. Small changes in input parameters can alter the entire outcome, causing studies of Stevenson 2-18 to differ significantly. One team prioritizes matching observed luminosity, accepting uncertainties in radius. Another focuses on surface temperature to interpret infrared data. There is no single correct model, only models that fit observations better or worse, producing testable predictions and illuminating the deep mysteries of stellar physics. In science, complexity is the norm. Large systems rarely submit to simple analysis. You must approach from multiple angles, gradually narrowing the range of possibilities. Today, the radius of Stevenson 2-18 is estimated one way. Tomorrow, as distance measurement techniques or atmospheric models improve, that number may change. This is not failure, but progress. Knowledge becomes more refined, accurate, and useful for predicting the future. Imagine observing Stevenson 2-18 up close, just a few astronomical units away, roughly the distance from Earth to the Sunday. The star is no longer a tiny point of light, but a colossal red wall filling the field of view. Its surface is uneven. Convective cells, each larger than Earth's orbit, create alternating bright and dark patches with a turbulent, chaotic atmosphere. Material rises in hot currents, cools, and falls back, forming circulations driven by the star's internal energy. Unlike the Sun, whose convective layer is thin, a red supergiant has convection almost throughout its volume. Up close, you would see even the material being lost. Gas streams and clouds, illuminated by starlight, drift outward along complex structures. Sometimes the flow is steady, sometimes violent, responding to internal structural changes. Dust grains form in cooler, outer regions, creating hazy veils that obscure the surface. Maser spots appear where conditions amplify specific wavelengths. Temperature is still clear. Though relatively cool for a star, its enormous size produces a tremendous radiative output. Any observational platform would require strict shielding, or it would vaporize. Most of the energy is emitted in the infrared, explaining the importance of ground-based infrared telescopes. Surface gravity is surprisingly weak. Despite a mass roughly 25 times that of the Sun, the enormous radius results in surface gravity lower than Earth's. Material does not need much speed to escape. This explains why mass loss is easy. The outer layers are barely bound. Any oscillation, convection, or radiation pressure can push material past the escape threshold. Weak gravity also affects atmospheric structure. It stretches far from the nominal surface, transitioning gradually into the surrounding envelope without a clear boundary. Determining where the star ends and space begins becomes arbitrary. Astronomers use an optical depth threshold to define a surface. where gas becomes transparent at a given wavelength. But this is a measurement convention, not a physical surface like Earth's ground. If you survived in such an environment and made measurements, the physics would emerge. Pressure, density, and temperature all obey the laws of thermodynamics and hydrostatics. Chemical composition reveals the history of nuclear reactions. Isotopic ratios indicate which reactions occurred in the core and how elements were mixed throughout the envelope. You could even detect neutrinos streaming from the core, carrying information about deep nuclear fusion. Unlike photons, which take thousands of years to travel from the core to the surface, neutrinos interact almost negligibly with matter, escaping directly and providing a real-time window into the star's interior. Detecting nuclear reactions deep within a star requires highly sensitive instruments. They can confirm whether Stevenson 2-18 is still burning helium or has moved on to heavier elements such as carbon or oxygen. Magnetic fields may exist around the star, but they are neither strong nor well organized like those in smaller stars. On the Sun, magnetic fields are generated by dynamo processes in the convective layer. In red supergiants, convection extends throughout nearly the entire volume, and theory suggests that magnetic fields are generated as well, but the details remain mysterious. Observations suggest weak, chaotic fields that may influence mass loss streams, producing the asymmetries sometimes seen in the surrounding envelope. Back in reality, Stevenson 2-18 lies 20,000 light-years away. We observe it with ground-based telescopes and occasionally with orbital instruments. Each observation adds another piece to the overall picture. Infrared photometry tracks brightness variations. Spectroscopy reveals chemical composition and velocities. Interferometry measures angular size. Radio observations record mass ejection. Together, these create a complete picture of a star we will never physically reach. But the star is not static. Stevenson 2-18, like most red supergiants, does not maintain a constant brightness. It pulsates, expanding and contracting over periods of hundreds or even thousands of days. These oscillations are not perfectly periodic. They are semi-regular, with amplitude and frequency varying over time. When the star expands, it becomes larger and cooler. When it contracts, the surface is slightly hotter. Estimates of its size depend on the timing of the observation. Theoretical models can only partially reproduce the characteristics of these pulsations. A major cause is likely changes in atmospheric opacity. As temperature varies, the gas becomes more or less transparent to radiation, affecting energy escape, which in turn feeds back on temperature and pressure, driving oscillations. But add convection, rotation, and mass loss, and complexity increases rapidly. Some researchers suggest that irregular pulsations may trigger strong mass loss events. An especially strong oscillation could expand the atmosphere, lower its density, and allow radiation pressure to accelerate material past the escape velocity. Repeated cycles could remove significant mass in a short time. Evidence comes from observations of the envelopes surrounding other red supergiants, suggesting that mass loss occurs in episodes rather than continuously. Stevenson 2-18 may also be undergoing such episodes. Its strong infrared excess indicates substantial dust in the surrounding envelope, consistent with recent or ongoing mass ejections. Whether this represents a normal state or a temporary phase remains unclear. Monitoring over many years or decades would reveal trends, but funding for long-term programs is often difficult to secure, competing with newer, more appealing projects. A larger question remains: how do such massive stars form in the first place? Initial mass determines the evolutionary path. Stars born with at least 8 solar masses will eventually explode as supernovae. Those above 25 solar masses may collapse directly into black holes. But for stars with initial masses of 30, 40, 50 solar masses or more, formation faces additional, extraordinary challenges. Within massive molecular clouds, where gas is so dense that gravity becomes a supernatural force, particles begin to coalesce, forming protostellar cores. As mass increases, the core heats up, and pressure and temperature reach the point where nuclear fire ignites. But for extremely massive stars, the radiation generated by fusion becomes a barrier, preventing further accretion, imposing an apparent limit of roughly 150 to 200 solar masses. Strangely, observations occasionally reveal stars exceeding this limit, as if they found alternative paths, merging with smaller stars or forming in low metallicity environments where radiation pressure is weaker. Stevenson 2 to 18, one of these wonders, began with 3040 m, and over its 17 million year life, it grew, leaving the hot main sequence layer to become the red supergiant we observe today. That journey involved burning hydrogen, expanding as its core shifted to fusing heavier elements, losing mass through stellar winds, while material processed deep within was transported to the surface. Now, the star exists in a fragile state, balanced between the outward push from nuclear reactions and the inward pull of gravity. It slowly consumes the remaining fuel, awaiting the moment when that balance will collapse. When the core can no longer sustain fusion, collapse occurs as supernova erupts, shining brighter than entire galaxies, leaving behind a neutron star or a black hole. That moment, the supernova itself remains mysterious. The iron core contracts rapidly under gravity. Electrons are forced into protons, forming neutrons and emitting neutrinos. In a brief second, the core shrinks from Earth size to only about 20 kilometers, reaching nuclear densities. The outer layers, stripped of support, plummet onto the neutron core at nearly the speed of light, collide, and rebound. A colossal neutrino flux combined with the rebound blasts the star apart in a Type II supernova. Yet, computer simulations show that things are not simple. Early attempts failed. Matter piled onto the neutron core without sufficient rebound. Researchers refined the code, adding neutrino physics, magnetic fields, rotation, and detailed core structure. Today, simulations can produce explosions, but the blade still hovers over the edge. A tiny change in initial conditions, a minute difference in rotation rate, or neutrino opacity, is enough to determine whether the supernova succeeds or if the star collapses quietly into a black hole without a brilliant flash of light. A massive star sometimes ends quietly, collapsing into darkness without anyone noticing unless we are observing at that exact moment. Stevenson 2 to 18, with its enormous mass and characteristic composition, is likely to explode spectacularly, yet certainty remains elusive, as if its fate is still undecided. When it does erupt, the energy released in an instant will far exceed the total energy of the entire star cluster, producing light strong enough to travel 20,000 light-years. From Earth, it may initially appear as a moderately bright star in the Scutum constellation for several weeks, before gradually fading over months. The explosion ejects most of the star's material, scattering heavy elements into the interstellar medium elements beyond iron, formed only in these extreme moments. Gold, platinum, uranium, all owe their existence to supernovae and similar cataclysms. The debris spreads outward, driving shock waves that compress nearby gas clouds and potentially trigger the birth of new stars. The remaining core will become either a neutron star or a black hole, depending on the mass that falls back after the initial rebound. A neutron star is a strange stellar remnant, so dense that a teaspoon of its material weighs billions of tons on Earth. They spin hundreds of times per second, generating strong magnetic fields and emitting radiation pulses, sometimes as periodic pulsars, sometimes as magnetars, with magnetic fields millions of trillions of times stronger than Earth's, occasionally flaring and shining across the galaxy in gamma rays. If the mass is too great, the neutron star will collapse further, forming a black hole, a region of gravity so strong that even light cannot escape. Stevenson 2 to 18's black hole is expected to have roughly 10-20 solar masses after accounting for mass lost through stellar winds and the supernova explosion. Stevenson 2 to 18's life spans millions of years, from a molecular cloud collapsing into a protostar, entering the main sequence, expanding into a red supergiant, and finally exploding as a supernova, ending in seconds as a neutron star or black hole. The contrast between long periods of stability and the instant of collapse captures the tragic grandeur of stellar evolution. Our Sun will never witness such a fate. It lacks the mass to become a red supergiant or explode. In 5 billion years, it will expand, engulf the inner planets, gently shed its outer layers to form a planetary nebula, and its core will contract into a white dwarf, cooling gradually over billions of years. Instead of ending violently, massive stars live fast, shine bright, and die violently. Stevenson 2-18 is an extreme exemplar, gigantic, brilliant like a small galaxy, constantly unstable, and destined to explode with an intensity that ensures a significant portion of the observable galaxy will witness it. If Stevenson 2-18 were hollow, the entire region of the inner planets of the solar system could fit inside it with room to spare. The radius of this star is roughly 2,000 times that of the Sun, and its surface area is equivalent to about 40 million Earths. Numbers like these make intuition almost useless. Imagine standing on a hypothetical planet, orbiting at a safe distance. In the sky, a deep crimson sphere would dominate a large portion of the view. Its edge would not appear sharp but would gradually fade into space due to limb darkening. Occasionally, that enormous surface would pulse slowly, then hurl gigantic clouds of gas outward, glowing as they catch radiation from the star itself. The sight would feel both alien and unsettling. A swollen, dark red celestial body that seems almost to breathe. Move a little closer, and tidal forces would tear any planet apart. Move farther away, and the light would become too faint. Yet even at the most ideal distance, life would have little chance. Intense radiation, powerful stellar winds, and the short lifespans of massive stars make biological evolution nearly impossible. Before multicellular life could even begin, the star would already be nearing its end. Life requires more ordinary stars, middle-aged yellow dwarfs like our Sun, burning steadily for billions of years. Massive stars are like the fireworks of the universe, brilliant but brief, and it is precisely their violent endings that nourish the galaxy. When they die, they scatter heavy elements into space, the very materials needed to form planets and life. Without generations of massive stars being born and dying, enriching the interstellar medium, the universe might still consist only of hydrogen and helium. No carbon for organic chemistry, no oxygen for water, no silicon for rock, no iron for planetary cores. Earth itself was formed from the ashes of dead stars. The calcium in our bones, the iron in our blood, the oxygen in every breath, all were forged in the cores of massive stars and thrown into space when those stars ended their lives. In that sense, stellar evolution becomes unexpectedly personal. We are literally made of stardust, descendants of nuclear fusion in ancient stars. When Stevenson 2-18 finally explodes, the material swirling through its vast atmosphere may someday become part of planets that do not yet exist, or of living beings that will arise billions of years from now. One day, those atoms might lie in the oceans of a distant world, or inside the body of a future life form. That cosmic cycle of matter recycling stretches across space and billions of years, connecting everything together. Within our galaxy, Stevenson 2-18 is not entirely alone. Red supergiants are uncommon, but not rare. Perhaps thousands of such stars exist in the Milky Way at any given time, though most are too distant or hidden behind dust to be easily observed. Each is a giant nearing the end of its life, destined to explode within the next few million years. They do not appear randomly. Massive stars are usually born together in clusters formed from the same molecular cloud. Over time, galactic motion and gravitational interactions slowly disperse them, but traces of their shared origin remain. The Stevenson 2 cluster contains many red supergiants, pointing back to a moment about 17 million years ago, when a violent burst of star formation created these colossal stars that are now entering the final chapter of their lives together. In the next few million years, the giant stars within the Stevenson 2 cluster will gradually enter the final chapter of their lives. One by one, they will explode, a sequence of supernovae unfolding over a relatively short cosmic time. Each explosion not only ends a star but may also trigger the birth of new ones, as shock waves sweep through nearby gas clouds and compress them enough to begin the process of star formation. That cycle has been repeating since long before the Sun existed. More than 13 billion years ago, when the Milky Way was still forming, the first stars were born in a universe composed almost entirely of hydrogen and helium, the direct remnants of the Big Bang. They lived brief lives and died, and in their deaths they enriched the interstellar medium with heavier elements. Later, generations of stars inherited that material. Because of it, rocky planets could eventually form, and much later, life itself could arise. We live in an era when many cycles of stellar evolution have accumulated enough heavy elements to build complex worlds like Earth. If star formation continues in the distant future, later generations of stars may become even richer in metals. Yet the universe has limits of its own. As space continues to expand, and the supply of gas is gradually consumed by star formation and stellar remnants, the process of star birth will slow and eventually cease. About 1 trillion years from now, the last stars will fade, leaving behind a dark universe dominated by stellar remnants, white dwarfs, neutron stars, and black holes. The explosion of Stevenson 2 to 18 will occur long before that time. Yet, it is still part of a much larger story. The journey of the universe from the hot, dense state of the Big Bang toward a cold, diluted future where even the light of the last stars will fade away. In that vast picture, every star, no matter how enormous, is only a temporary structure, a small whirl in the cosmic flow, existing briefly before dissolving back into the shared matter of the universe. Stevenson 2 to 18 may be one of the largest stars we have ever discovered, but even it is finite, and it will die. Its entire life, from formation to supernova, is only a blink in the history of the universe. The cosmos was already ancient before this star was born, and it will continue long after its remnants cool and fade into invisibility. That scale makes astronomy both overwhelming and humbling. We observe these magnificent objects, measure their properties, marvel at the limits of nature, yet ultimately they too are transient structures. And so are we. The difference lies only in timescale. Humans live for a few decades. Stars live for millions or billions of years. Galaxies persist for tens of billions of years. Yet all of them are temporary patterns in space-time, born from the interaction of fundamental forces and destined eventually to dissolve. Does that diminish the meaning of existence? Perhaps the opposite. Stevenson 2 to 18 exists right now, shining brilliantly even though its fate is already sealed. We also exist right now, with the ability to observe and understand a star tens of thousands of light years away. Impermanence does not make these things meaningless. It makes them precious. When Stevenson 2 to 18 finally explodes, the explosion will be both violent and creative. The star's matter will not disappear. It will simply change form. Its atoms will be hurled into space, cool, mix with interstellar gas, and one day become part of new star-forming regions. From there they may become part of new stars, new planets, perhaps even new forms of life, if conditions allow. The cycle of matter continues, guided by gravity, nuclear fusion, and the fundamental laws of physics, unfolding across timescales far beyond human intuition but still understandable through observation and mathematics. The ability to understand this is one of humanity's greatest achievements. Only a few centuries ago, stars were merely mysterious points of light in the sky. Today we can analyze their composition from distances of hundreds or thousands of light years. We can model their internal structure and predict their futures. We know that some stars are thousands of times larger than the Sun, that they consume their fuel at astonishing rates and end their lives in catastrophic explosions. We know the temperature of Stevenson 2 to 18, its luminosity, and the rate at which it is losing mass. We understand the nuclear reactions powering it, the physical laws shaping its structure, and the evolutionary path that brought it to its current state. That knowledge did not appear overnight. It is the result of generations of astronomers, people who built better telescopes, developed deeper theories, and continuously tested them through observation. Understanding massive stars is far from simple. It requires physicists to decode nuclear physics, master quantum mechanics, and solve the equations governing stellar structure. Decades of international collaboration, data exchange, and the passing of ideas between generations of astronomers have built a coherent picture of stellar evolution, explaining countless observations and providing testable predictions. Of course, that picture still has gaps, especially for extreme stars like Stevenson 2-18. This star pushes every boundary. Enormous size, high mass loss rates, unpredictable variability, and excess infrared radiation that reveals complex atmospheric dynamics we are still trying to fully understand. These extremes do not overturn fundamental theory. They simply show that nature utilizes the full range of possibility, creating objects at the edge of what is physically achievable. Every anomaly is an opportunity to learn, a reminder that theory must be tested and refined. That process never stops. New high-resolution telescopes probe obscured regions, missions like Gaia measure distances more precisely, and computational models grow increasingly sophisticated. Each advance clarifies our view, but also uncovers complexities never seen before. Observations are far from easy. Stevenson 2-18 hides within dense clouds of dust, with most visible light absorbed, leaving only infrared radiation carrying information about the star's properties. But the dust distorts the data. It absorbs selectively at certain wavelengths, re-emits at lower temperatures, producing excess infrared. Determining the star's true emission requires sophisticated modeling and multi-wavelength observations. Its estimated distance, about 20,000 light-years, carries significant uncertainty, possibly 50% or more. Distance directly affects calculated luminosity, which in turn is closely tied to stellar size via the Stefan-Boltzmann law. Errors in distance propagate through every inferred physical property. These issues are not unique to Stevenson 2-18. Scutum was once estimated at 1,700 solar radii. After better distance measurements by Gaia, its radius dropped to roughly 900. Such adjustments are normal. Previous numbers were not wrong. They were the best estimates at the time. Science progresses through refinement, not through perfection from the start. Whether Stevenson 2-18's radius is 1,800 or 2,150 solar radii, it remains an extreme, unstable star approaching the end of its life. The general model still holds. Massive stars evolve quickly, swell dramatically, lose mass violently, and ultimately explode. The details may shift, but the overall picture remains consistent. This also reveals a fundamental truth about stellar physics. There is a natural limit to expansion, the balance between gravity and radiation pressure. When luminosity is too high, radiation pressure on the outer layers exceeds gravitational pull. Material is blown away, increasing mass loss rates. Stevenson 2-18 appears to be testing this limit. Mass continues to be ejected, evidenced by excess infrared and strong emission lines. Mass loss before the explosion shapes the star's ultimate fate. Less material in the core during collapse means the supernova will differ. Its dynamics, remnants, and chemical yields will vary accordingly. It is this process, unfolding before the final moment, that determines what will be dispersed into space to enrich future generations of stars and planets. Understanding stellar evolution cannot be achieved by observing a single star. The process unfolds over millions of years. Instead, astronomers observe many stars at different stages, piecing together a composite picture. In that picture, Stevenson 2-18 represents a single data point, an extreme red supergiant captured at a specific moment in time. The other stars in the Stevenson 2 cluster provide additional context. They are coeval, but have different masses, and therefore occupy different evolutionary stages. The most massive stars have already swelled into red supergiants, while the lighter stars remain steadily on the main sequence. By observing the entire population, stellar evolution models can be tested. From the main sequence to red supergiant to supernova, the overall picture aligns with reality, even though many details still require refinement. Stevenson, 2-18, is not only massive but also complex. It exhibits cyclical variability. Its outer layers expand and contract. Material heats up, cools, and falls back, producing pulsations that can last months or even years. These oscillations can sometimes be strong enough to distort the star's shape and even eject material into space. Some of the ejected material condenses into dust, forming a thick infrared envelope around the star. Such circumstellar shells are common in red supergiants. They make direct observation difficult, but they are also sites of chemical activity. Molecules and dust form in the cooler outer regions, then are carried away by stellar winds and radiation pressure. This environment is dynamic and complex, very different from the simple photosphere of a main sequence star. Understanding this system requires multiple techniques. Infrared imaging maps dust distribution. Spectroscopy identifies molecules. Interferometry reveals spatial detail inaccessible to single telescopes. Mass loss emission traces the physical conditions in the surrounding gas. Taken together, Stevenson 2-18 emerges as a dynamic entity, constantly changing over timescales far longer than a human lifetime. Material continuously streams outward, carrying mass and energy. The stellar radius fluctuates with the expansion and contraction of the outer layers. What we observe on the surface originates in the core. Fusion in the core generates energy, producing pressure that prevents the star from collapsing. Fusion rates depend on temperature and composition. As helium accumulates, fusion shifts to heavier elements. Carbon, oxygen. Each stage proceeds faster and at higher temperatures, with the star's structure continuously adjusting. In extreme stars like Stevenson 2-18, evolution occurs at astonishing speed. A star, 25 times the mass of the Sun, may become a red supergiant in just a few million years, a blink compared to the 1.0 billion year lifespan of a star like the Sunday. Higher core temperatures, faster fusion, and stronger luminosity mean fuel is consumed more rapidly. A brighter candle burns faster. It is this rhythm that explains the dizzying pace of evolution in these red giants. Stevenson 2-18 is not only a red supergiant, but also a dynamic system, continuously undergoing cycles of expansion and contraction. During these phases, it occasionally ejects significant amounts of material, creating multiple circumstellar shells, each recording an episode of mass loss. Observing these layers is like reading the star's recent diary, revealing its history and hinting at its future evolutionary path. The amount and rate of mass loss determine not only Stevenson 2-18's individual fate, but also influence the galaxy at large. They allow astronomers to predict supernova rates, the formation of neutron stars or black holes, and the chemical enrichment of the interstellar medium. Massive stars are rare, yet their power shapes the environment, triggering new star formation while disrupting neighboring clouds. When Stevenson 2-18 explodes, it will participate in all of these processes, but the exact nature of the future explosion remains an open question. Will it be a typical core collapse supernova, a violent hypernova, or will it collapse directly into a black hole without a brilliant display? All depends on the remaining core mass, rotation rate, and magnetic field parameters difficult to measure directly. We can only observe the current state: luminosity, temperature, mass loss rate, and temporal variations. These observations allow inferences about the core structure and stellar evolution. Stevenson 2-18 has passed the hydrogen burning phase, is fusing heavier elements, and core instability will increase as fusion progresses toward increasingly unstable nuclei. In the next few million years, the conclusion will arrive. The core will collapse in mere seconds, releasing more energy than the Sun produces over its entire lifetime. The outer layers will be blown away, forming an expanding remnant lasting tens of thousands of years. At the center, the remnant will become either a neutron star compressed like a nucleus or a black hole, where matter is so dense that even light cannot escape. Both outcomes place matter under extreme conditions, governed by physics that exists almost exclusively in these environments. Though details remain uncertain, we understand that everything currently occurring in the core determines the star's ultimate fate. Stevenson 2-18 exemplifies a fundamental cosmic cycle. Matter accumulates into a massive star. Fusion transforms light elements into heavier ones and releases energy. The star temporarily resists gravity, and then, when fuel is exhausted, the core collapses and the explosion disperses material back into space. That material will later coalesce into new stars, continuing the cycle. This process has repeated for billions of years, gradually enriching the universe from its original hydrogen and helium. Supernovae create subsequent generations of stars, chemically enriched and complete with the full periodic table. Currently, Stevenson 2-18 continues to synthesize elements in its core. When it explodes, those atoms will travel across light years, contributing to the formation of stars, planets, and potentially life in the distant future. And we, composed of material that once endured the extreme temperatures and pressures inside ancient supernovae, temporarily exist as conscious beings capable of understanding our own origins. This is the deepest connection between humans and giant stars like Stevenson 2-18. We are not separate from the universe. We are its product. Every element heavier than helium in your body once existed inside a star. Calcium in your bones, iron in your blood, carbon forming your cells, all were created in stellar cores or in violent supernova explosions. We are, in fact, made of stardust. As Carl Sagan once said, recognizing this connection transforms how we perceive both ourselves and the universe. We are not detached observers, merely standing outside to watch distant phenomena. We are part of cosmic evolution, temporary structures formed from matter shaped by generations of stars that lived and died, creating the chemical complexity necessary for life. Stevenson 2-18 is a present link in that chain, a vivid example of processes operating across the history of the universe. When Stevenson 2-18 explodes, it will create new elements and scatter them across space. One day, those elements may become part of new planetary systems, potentially nurturing life. Distant beings in the future might look up at their night sky, see larger stars, and wonder about their cosmic origins just as we do today. That cycle has never stopped. Viewed this way, consciousness itself repeatedly emerges from matter arranged by physical laws, unfolding over endless time. When we observe Stevenson 2-18, we are not seeing an isolated object. We are witnessing a moment in an eternal process, connecting past, present, and future across cosmic timescales. The star exists right now in a specific evolutionary state, but that state originates from conditions set billions of years ago, when the galaxy was young and different. The matter composing Stevenson 2-18 was inherited from previous generations of stars, which created heavy elements through fusion and dispersed them via supernovae. Those metal-rich gas clouds eventually collapsed under gravity, forming new stars, including the Stevenson 2 cluster. This recycling process has operated continuously since the first stars formed about 13 billion years ago, each generation adding complexity to the cosmic chemical reservoir. The earliest stars contained only hydrogen and helium and could not form rocky planets. When third-generation stars exploded, they seeded space with carbon, oxygen, magnesium, silicon, and iron. Second-generation stars incorporated those elements and produced even heavier elements. After countless cycles, the interstellar medium now contains the full periodic table, all created through fusion and supernovae. Stevenson 2-18 formed from that enriched material, though its precise composition still holds some uncertainties due to observational limits. The rate of enrichment varies across the galaxy. Central regions, where star formation was historically higher, produced metal-rich stars like Stevenson 2-18. Metals in the star subtly influence its evolution. Atmospheric opacity, mass loss rates via stellar winds, internal convection. Higher metallicity is often accompanied by greater mass loss. One reason Stevenson 2-18 continuously ejects material despite its relatively young age. Understanding this star requires considering multiple factors simultaneously. Surface temperature determines the photon wavelengths emitted. Luminosity reflects total energy output. Mass loss rate affects long-term evolution. Internal structure governs stability. Each factor is tightly coupled to the others through the laws of physics. Together, they form a living, dynamic entity, a crucial link in the ongoing cosmic cycle, which we, through consciousness, are fortunate to perceive. The intense radiation pressure from Stevenson 2-18's immense luminosity drives material outward, causing continuous mass loss. As the mass decreases, the gravitational force in the core weakens, altering nuclear reaction rates and energy output. This is a complex system, where every change propagates throughout the star's structure. To understand it, astronomers must build sophisticated computer models, attempting to simulate these interactions through physical equations. Modern stellar evolution codes account not only for nuclear reactions but also for radiative transfer, convection, stellar winds, and rotational effects. Researchers input initial conditions: mass, composition, rotation rate, and allow the model to predict the star's trajectory over millions of years. These models successfully reproduce many observable properties, enabling predictions of the evolution of extreme stars like Stevenson 2-18. But no model is perfect. Some physical processes remain incompletely understood. Convection is turbulent and difficult to simulate, and the mechanisms of mass loss in massive stars are complex and approximated. Small errors accumulate over evolutionary timescales, making it impossible to say with certainty whether the star will explode in 10,000 or 100,000 years. Overall, the current state of Stevenson 2-18 is clear: enormous, luminous, strongly evolving, and unstable. Its fate seems inevitable: a supernova, most likely leaving behind a black hole. The precise timing depends on the remaining core mass, the mass loss rate, and internal mixing processes, all of which carry uncertainties. This difficulty is compounded by observational limits. Thick dust surrounding the star blocks visible light. Next-generation infrared telescopes can penetrate this dust. Interferometers measure angular diameters directly, and long-term monitoring programs collect variability and spectroscopic data. Step by step, these observations refine models, gradually illuminating the star's evolution. Theoretical understanding advances in parallel. More powerful computers allow sophisticated simulations. Laboratory experiments and quantum calculations provide more accurate nuclear reaction rates, and observations of other massive stars at different evolutionary stages help apply generalized knowledge to Stevenson 2-18. Gradually, the picture becomes clearer, though absolute certainty remains elusive. This is how science progresses. Initial observations reveal phenomena to explain, preliminary theories arise, predictions are tested, subsequent observations refine or refute them, and theories improve. This cycle repeats endlessly, each iteration deepening understanding without ever fully concluding. Stevenson 2-18 exemplifies this process perfectly. We know far more about it than when it was first catalogued, yet fundamental questions remain unanswered. And it is the star's extreme nature, colossal mass, extraordinary luminosity, violent mass loss that challenges stellar physics, pushing it to its outer limits and allowing the basic mechanisms of stellar physics to be tested rigorously. When what we observe does not match predictions, it signals gaps in our understanding, hinting at physics yet to be discovered. Stevenson 2-18, relatively close to us, provides a vivid example of physical processes occurring throughout the universe. Similar giant stars exist in galaxies millions or even billions of light-years away, but they are too distant for detailed study. Understanding nearby stars like Stevenson 2-18 helps establish principles applicable across the cosmos, forming the foundation for interpreting stellar populations at any distance and time. Explosions of massive stars do more than enrich a galaxy chemically. They also regulate star formation. Shock waves compress nearby gas clouds, triggering new stars, while simultaneously dispersing and heating gas, slowing star formation elsewhere. This delicate balance shapes the structure and evolution of a galaxy over billions of years. Moreover, a supernova like Stevenson 2-18 could produce gravitational waves if its core collapses asymmetrically, propagating across space at the speed of light. Current instruments have already detected gravitational waves from merging black holes and neutron stars. A nearby explosion could provide unprecedented data on deep core processes. By combining multiple messengers, light revealing the surface and atmosphere, neutrinos probing core activity, and gravitational waves tracing matter, motion, and asymmetry, we can construct a comprehensive picture that no single observation alone could provide. Multi-messenger astronomy has become the new frontier of research. Observing a future supernova, for example Stevenson 2-18, if it explodes soon, could simultaneously exploit all channels, revolutionizing our understanding of stellar death. The exact timing remains uncertain. In astronomical terms, soon could mean thousands of years. From a human perspective, Stevenson 2-18 might remain in its current state across many generations, or it could explode tomorrow. This uncertainty makes precise prediction difficult, but emphasizes that stellar evolution occurs on timescales far beyond human life. We can only observe moments, snapshots of a process that spans millions of years. The temporal gap between human observation and stellar evolution presents an intriguing challenge. We cannot watch a star from birth to death. Instead, astronomers observe many stars at different stages, piecing together a continuous evolutionary sequence. It is like trying to understand human aging by looking at photos of many people at different ages, without ever following anyone's growth directly. This method works well, confirmed by the consistency of many observations, though it never provides absolute certainty. Stevenson 2-18, the current link in the chain of cosmic evolution, will one day become an invaluable data point. When it explodes, astronomers around the world will immediately observe the event across all available wavelengths and instruments, testing predictions about the deaths of giant stars, the mechanisms of supernovae, nucleosynthesis processes, the resulting remnants, and impacts on the galaxy. Until that moment, the star slowly marches toward instability. Its fusion core produces heavier elements, while the outer layers expand and contract according to internal dynamics we only partially understand. Material continuously escapes the star, drifting back into interstellar space. Deep within, the iron core gradually accumulates, approaching a critical mass where collapse becomes inevitable. When that moment arrives, whether in a few years or thousands of millennia, the explosion promises to be spectacular. Even 20,000 light-years away, the supernova could shine brighter than the entire Milky Way for weeks or months, potentially visible during the day under the right conditions. The explosion will create a brilliant nebula lasting thousands of years, rivaling famous remnants like the Crab Nebula in complexity and beauty. At the center, a black hole will remain, marking the location of the once mighty star. That black hole becomes a study object in its own right. Its mass reveals information about the progenitor star. Its spin reflects angular momentum from the core collapse. And if the explosion is asymmetric, its orbit through space will tell a story about the dynamics of the blast. Even after the supernova's light fades, the remnant continues to hold immense scientific value. This is Stevenson 2-18's ultimate legacy. Long after humanity is gone, and Earth becomes uninhabitable billions of years from now, the black hole and the heavy elements produced by the star persist. The black hole continues orbiting the galaxy indefinitely, occasionally interacting with other objects, slowly evaporating via Hawking radiation over timescales that make the current age of the universe feel fleeting. The star is temporary, yet leaves a lasting mark. Stevenson 2 to 18 was assembled from gas clouds once belonging to other stars, and when dispersed, that material will be reborn into new stars, planets, and perhaps life itself. The heavy elements endure, incorporated into later structures. We participate in that cycle. The atoms in your body once experienced the death of a star billions of years ago, passed through gas, dust, rock, and biological molecules, and temporarily coalesced into you. One day, they will disperse again, recycled into new forms beyond imagination. The universe wastes nothing. Every atom is reused endlessly, forming increasingly complex structures through cosmic evolution. Stevenson 2 to 18 represents a grand chapter in that eternal story, a link in the endless cycle, inscribing past, present, and future into the very substance of the universe. A chapter is approaching a dramatic conclusion before a new cycle begins. Seen from 20,000 light-years away, Stevenson 2 to 18 appears as a star that our simplest models would suggest cannot exist, yet clearly does. A giant, bloated, unstable star, it challenges every assumption about the limits of stellar structure. That is what makes it significant. Even though estimates of its radius remain puzzling 2,150 or 1,800 times the Sun's radius, its existence transcends precise numbers. Different studies produce varying results depending on assumptions about distance, temperature, or dust composition. Future observations with more advanced instruments will refine these numbers, possibly naming a new champion, like NML Cygni, or a hidden giant in an obscured region. But the critical point is not the exact size, it is the very existence of such extreme objects. Stevenson 2 to 18 exemplifies stellar evolution pushed to the extreme. It demonstrates that nature explores the full range of physical possibilities, creating structures at the edge of stability. Stars at these extremes serve as living laboratories, testing theories under conditions that cannot be replicated on Earth. The temperatures, pressures, and densities inside Stevenson 2 to 18 exceed any laboratory experiment, and its mass loss rate, luminosity, and rapid evolution continuously challenge models. Every observation and refined measurement constrains theory, gradually reducing uncertainty. The star will explode perhaps in 1,000 years, perhaps in 100,000. The timing is still unknown, but the outcome is nearly inevitable. When its core collapses, the supernova will outshine billions of ordinary stars, potentially observable across the galaxy even through dust. Astronomers will monitor it with instruments far more sophisticated than we currently possess, collecting data that today we can only dream of. Such observations will answer questions we have not yet even asked. Until then, Stevenson 2 to 18 persists in a fragile state, fusing heavy elements in its core, losing mass through powerful stellar winds, and pulsating according to internal dynamics. It simultaneously creates and destroys itself, building heavy elements through fusion while stripping away its outer layers. The interplay between these two processes determines the star's remaining lifetime and the type of remnant it will leave. The broader context matters more than any individual object. Stevenson 2 to 18 exists within a cluster of red supergiants, all roughly the same age, each approaching the brief conclusion of its life. In the next few million years, this cluster will experience multiple supernovae as the largest members explode in succession. Those explosions will enrich the interstellar medium with heavy elements, while triggering the formation of new stars as shock waves compress nearby gas clouds. This cycle has operated since the first stars formed more than 13 billion years ago. Each generation produces heavy elements through fusion and disperses them via supernovae. The next generation incorporates those elements. Rocky planets only become possible after multiple generations of stars have enriched the interstellar medium with silicon, iron, and magnesium. Life itself emerges only after billions of years of chemical enrichment, providing essential elements such as oxygen and phosphorus. You exist because stars like Stevenson 2 to 18 lived and died billions of years ago, creating the elements present in your body. The calcium in your bones is a product of nuclear fusion in stars. The iron in your blood was forged in an ancient supernova. The oxygen atoms in your body right now once embarked on a journey that began in the cores of massive stars, where they were forged in blazing thermonuclear reactions. When those stars exploded, oxygen and other elements were scattered across the cosmos, seeding planets and eventually becoming part of living organisms. We are not mere distant observers. We are active participants in cosmic evolution, temporary structures composed of stellar debris, aware of our own origins. The matter in your body has traveled through countless stars, ancient planets, and even biological molecules, in organisms that lived and died long before humanity existed. Today, Stevenson 2-18 continues that journey, producing new elements through nuclear fusion elements that may one day form a star, a planet, or even a future life form. When that star explodes, these elements will spread across light years, mix with other matter, and contribute to the formation of new cosmic structures. This cycle never stops. Matter is continually recycled, gradually building ever more complex structures under the invisible hand of physical laws. Massive stars also reveal secrets about how the universe operates. Gravity pulling inward and radiation pressure pushing outward determine the maximum size a star can reach. Stevenson 2-18 is testing that limit, existing in an unstable state where even a minor perturbation can trigger catastrophic mass loss. Signs such as excess infrared radiation and strong emission indicate the star is gradually self-destructing, preparing for its final collapse. Looking back to the early universe, population 3 stars may have been even more enormous than anything we see today, hundreds of times the mass of the Sunday. When they exploded, they produced unstable pair instability supernovae, obliterating themselves completely without leaving remnants. Stevenson 2-18 provides a glimpse into how extreme stars exist in the present era, helping us understand the mass limits that the first stars could achieve. Every observation of extreme objects today weaves another piece into the tapestry of cosmic history. The search for the largest star is far from over. New surveys will expand our view, measure distances more precisely, and model the complex effects of dust and stellar atmospheres. The title of largest star may change hands multiple times as new candidates emerge from the dark regions of the galaxy. The race to find the largest star is fascinating, but it's only the surface. More importantly, extreme stars like Stevenson 2-18 teach us how stellar evolution operates at the harshest limits. Gravity, nuclear fusion, radiation pressure, every force vying for dominance in these colossal spheres of fire, and together they write the story of heavy elements, the foundation for planets and life itself. In these natural laboratories, matter behaves in ways humans cannot replicate, and each star is a living experiment. Stevenson 2-18 may be the largest we know, but it is only one of many extreme stars scattered across the galaxy. Each star helps refine theoretical models, enriches the interstellar medium with heavy elements, and seeds future generations of stars. In their mere existence, they remind us of how much remains unknown. We cannot predict exactly when a star will explode. We do not fully understand how energy moves through its outer layers, and we cannot be certain whether the end will be a neutron star or a black hole. These gaps are not failures, they are evidence of the profound complexity of nature. Every answer gives rise to new questions. Every precise measurement reveals previously unexplained mysteries. Discovery never ends. Future astronomers will observe Stevenson 2-18 with instruments we have not yet invented, apply theories we cannot yet conceive, and ask questions we have not yet imagined. They will refine our observations, correct our errors, and smile at the simplicity of our current understanding. Then, one day, perhaps thousands of years from now, Stevenson 2-18 will explode. Future observers will record neutrinos streaming from its collapsing core, gravitational waves from asymmetric mass movements, radiation spanning radio to gamma. They will witness shock waves tearing through the star's outer layers, see heavy elements forged in the heat of the explosion, and watch a black hole form at the center. This event will simultaneously answer some questions and generate new mysteries, a moment of transition. Stevenson 2-18 will no longer be a star but a supernova remnant, ultimately leaving only a quietly spinning black hole orbiting the galaxy for millions of years. For now, the star remains in the night sky, invisible to the naked eye, yet blazing brilliantly in infrared. Its power equals hundreds of thousands of suns, illuminating the surrounding emptiness, slowly ending its stellar life, while scattering heavy elements that make cosmic complexity and eventually life possible. In the core of Stevenson 2-18, every second, nuclear fusion converts mass into energy, according to Einstein's equation. At the same time, stellar winds carry away matter at hundreds of kilometers per second, gradually pushing the star closer to its fateful moment, when fusion can no longer resist its own enormous weight, and collapse becomes inevitable. That moment will arrive. The exact timing remains uncertain, but the physics is clear. When it happens, as Stevenson 2-18 completes its brilliant but brief life, one of the most energetic events in the universe will unfold. A core collapse supernova, shining so brightly that, for an instant, it could rival the combined light of 100 billion stars. Yet even in death, the star's atoms do not vanish. They disperse, mingle with the interstellar medium, and eventually collapse under gravity to form new structures. This cycle continues, governed by the fundamental forces that have shaped cosmic evolution since the Big Bang. Matter gathers, coalesces, disperses, and reassembles endlessly. Stars are born, live short or long lives depending on mass, then die sometimes quietly, sometimes violently, always returning processed matter to the universe. This is the story of Stevenson 2-18, the largest star we know, a story that began 17 million years ago, when a dense patch in a molecular cloud collapsed. A story that will conclude with a spectacular explosion in the coming millions of years, both unique and universal. One star among hundreds of billions in the Milky Way, yet an extreme example revealing fundamental truths about stellar physics and cosmic evolution. The atoms that once made up this star will persist long after the supernova fades. They will become part of new stars, new planets, perhaps even new life, billions of years later. Future beings may look up at the sky and wonder about their origins, never realizing that some of the atoms in their bodies once belonged to Stevenson 2-18, a star that exploded millennia ago. Within this cycle, in the endless recycling of matter across cosmic time, perhaps we find the deepest meaning. Nothing is permanent, yet nothing is truly lost. Everything constantly changes form, while essence endures. Stars are temporary structures, planets too, living beings as well. But atoms persist, circulating through increasingly complex forms, telling the story of a universe that never ceases to unfold. And right now, Stevenson 2-18 exists somewhere in the constellation Scutum, 20,000 light-years away, radiating almost unimaginable energy, slowly destroying itself while creating elements that will outlast billions of years. It is both one of the most extreme objects in the galaxy and a necessary consequence of physical laws operating under extreme conditions. A phenomenon simultaneously extraordinary and inevitable, a product of stellar evolution pushed to the limits that physics allows.